Hi, in this video we're going to be doing section 4.1 on quadratic functions and transformations. So quadratic function just means a function that we can write in this form, where it's some number times x squared plus some number times x plus some constant at the end. And what we require is that there really is a non-zero number in front of x squared. The others can be zero if we want. They can be negative. They can be fractions. The idea is this is more complicated than a line. Right? If we had a linear function, an example would be something like y equals negative 2x plus 5. And basically the most complicated thing is x. In a quadratic function, the most complicated thing is x squared. So we could have something as simple as f of x equals x squared, f of x equals negative 1/3 x squared plus x minus 7, f of x equals 2x squared plus 5x minus 8. Anything where the most complicated thing you see is x squared, along with maybe x showing up and maybe a number, and then the rest is just add, subtract, multiply, divide. That's a quadratic function. And not always do they occur like this. This is what's often called standard form. Sometimes we will see them in a different form. But if we see a function where the most complicated aspect seems to be there's the variable x and it's getting squared, then that is quadratic. Because for this example, what I could do is I could expand it. X plus 1 squared means x plus 1 times x plus 1. When I FOIL that out, I get x squared plus 2x plus 1 minus 7. I can distribute the 3. And I can group like terms. And then after that work, it's in standard form. Something in front of x squared plus something with x plus or minus a number. You don't necessarily have to go through those steps. You can just look at this original and say, okay, I see the x, I see the squaring. This is quadratic. Now, the graph of any quadratic function is a kind of U-shaped graph called a parabola. Parabola is not a synonym for U-shaped graph. There are things that are shaped like a U that are not technically parabolas, but we don't have to worry about that distinction right now. So any parabola is going to be a transformed version of the parent graph y equals x squared. So I'm just going to make a little table here of very easy values for x and x squared. And I can plot them. So I will draw an x-axis like so, a y-axis like so. I will plot those points, so 0, 0, 1, 1, 2, 4, 3, 9. And if I connect these, I get a U-shaped graph that looks something like so. This point at the very bottom, essentially the symmetry point, is called the vertex. And then the vertical line that goes through the oops, I don't know how, I clicked on the wrong thing on my home iPad. Weird. And then the vertical line that goes through that vertex is called the axis of symmetry. That'll be the symmetry line for this parabola. The stuff to the left of that line looks like the stuff to the right. Now, for our purposes, what you really want to just know instantly, that y equals x squared has as its 3 easiest points negative 1, 1, 0, 0, 1, 1, and that it's U-shaped. If you know these facts, then you can put together a decent version of the graph of x squared. Don't worry about it being perfect. Don't worry about having tons and tons of points. You really just want a few easy and important points, and then you connect them into something that looks U-shaped. Because once we know what x squared looks like, we can start transforming it just like we've transformed everything else. So for example, if I have y equals 3x squared, I'm multiplying that function by 3. So I know this is like y equals x squared, but 3 times as tall. So if I want to have some idea of what that looks like, I'll create my x and y axes. If I had basic x squared, those would be my 3 easiest points. But I don't have basic x squared. I have something 3 times as tall. To graph something 3 times as tall, you literally just take each one of these points and you multiply its y-coordinate by 3. This point was at y equals 1. Let's multiply by 3. It's up here at y equals 3. So we have a point right here. The x-coordinate is 1. The y-coordinate is 3. We can do the same thing on the left. The y-coordinate was 1. I make it 3 times as tall without changing the x. This point here is at negative 1, 3. I had a point at the origin. If y equals 0, then multiplying by 3 still keeps it at 0. And now, just take those 3 points and connect them into something U-shaped, and then just make sure you indicate that you know it keeps going. You don't have to draw it perfectly, but if you have 3 easy points and an overall U pattern, that's a pretty good graph. This is what y equals 3x squared looks like. We could do y equals x squared minus 3. That's like y equals x squared. But if we subtract 3 outside the squaring, we shift down by 3 units. So again, my recommendation is just plot those 3 really easy points for the original y equals x squared. There they are. And let's imagine we just shift everything down 3 units. If I take the point on the right and shift it down 3 units, it's here. That's at 1, negative 2 if you want to label it. The point at the origin goes to 0, negative 3. The point on the left goes to negative 1, negative 2. And we'll just reconnect these into something that is roughly U-shaped with those 3 points. That is our rough graph of y equals x squared minus 3. We have 2 more. Y equals quantity x minus 2 squared. And y equals negative x squared. Here, what we're going to do is we're going to shift to the right 2 units because the subtraction is happening inside the function, inside the squaring. Don't get caught up on parentheses. It's not about being inside parentheses. It's about being inside the function. Squaring is the main function in x squared, so that minus 2 is inside the squaring. Plain old y equals x squared would have these 3 points. If I shift them 2 units to the right, they look like this, and I just connect into something vaguely U-shaped. Y equals quantity x minus 2 squared looks something like so. And then finally, a minus in front of a function turns it upside down. It reflects it across the x-axis. Regular old x squared has those 3 easy points. If we turn it upside down, they look like so. And now it doesn't really look like the letter U because it's upside down. It's an upside down U. But y equals negative x squared has that general pattern. 3 easy points and the pattern is enough. Now, it's possible for us to combine all of these in what's called vertex form. And if we really understand how all the transformations work, we can gather some information about the graph and graph it all at once. We don't have to think about this one transformation at a time. Here is pretty much the most generic way we could have a transformed version of x squared. We could have some number multiplying outside, some addition or subtraction inside, some addition or subtraction outside. In this version, we're going to assume we have x minus h inside and x plus k outside. And we'll temporarily pretend these are positive numbers. What has happened is that we have shifted h units to the right because we have x minus h inside those parentheses, and k units up. Our normal y equals x squared has its vertex at 0, 0. And what's nice about starting from 0 is that it's very obvious where things go. If I started at 0 and went over by h in the x direction and up by k in the y direction, then I wind up in a place where the x coordinate is h and the y coordinate is k. That will be the location of the vertex. So that's why we call this vertex form. If you look at this form, you can almost instantly identify where the vertex is. Do be careful about the positives and negatives. In this version, we're shifting right and up. If the positives and negatives are in a slightly different combination, maybe you're shifting down, maybe you're shifting to the left. But you can still identify the vertex almost immediately. And then the vertical line x minus h goes through that vertex. A controls the steepness and the direction. If A is positive, the parabola opens upwards. If A is negative, the parabola opens downwards. And A basically tells us, did we make this parabola taller, shorter, or leave it the same size? If you know you've made it 3 times as tall, you can adjust for that, especially if you're using the very easy points. So let's look at some examples. Suppose we want to graph this. Y equals -3 times x plus 1 squared plus 4. Right off the bat, I'm going to notice that we shifted 1 to the left and 4 up, which means the vertex will be at -1, 4. If you're following that original pattern very mechanically, you have to write this with a negative. So we have x minus -1. The x coordinate of the vertex is at -1. So I know where that vertex is. And now let's look at A. Because there's a negative here, I know this is a downward opening parabola. And because there's a 3 here, I know it's 3 times as steep as normal y equals x squared. So how would this be reflected in a graph? I don't even have a grid here. I guess I could copy one from. Let's temporarily erase this stuff and copy this grid. So I've created my grid. Let's put axes on here. So we'll say this is our x-axis. This is our y-axis. Our vertex is at -1, 4. So that is here. 1 to the left and 4 up. Now, from that vertex, I know I will have a downward opening parabola. I also know it will be 3 times as steep as the normal y equals x squared. And let's think about those really easy points for normal y equals x squared. We had one at 0, 0. We have one at 1, 1. We have one at -1, 1. From the vertex to those really easy points, it's 1 over 1 up. 1 over 1 up. If this is 3 times as tall and upside down, it won't be 1 over 1 up. It will be 1 over 3 down. So 1 over and 3 down gives us a point here. 1 over 3 down gives us a point here. Only do this for one set of points. This isn't like slope where you can repeat it over and over again. But these will be the 3 easiest points on this graph. We figured out where the vertex is, and then we're just drawing 2 more points to reflect that it's 3 times as tall. And then we just connect this into a U-shape. Remember that it's rounded. This is not like absolute value, which is perfectly linear. There's a roundness to this. The sides are slightly curvy, not perfectly straight, and it's very curvy around the vertex. There's no corner there. This is not a beautiful picture, but it's close enough. We understand where the vertex is. We understand the steepness. We understand it points down. Here's another example for you to try. If you're watching this for the first time, really do pause and try the same things. For this one, the vertex will be at 3, 1 because we've shifted 3 to the right and 1 up. It opens upward, but it's 2 times as steep as normal y equals x squared. So let's try to draw that. I'll add an x-axis, I'll add a y-axis. My vertex is at 3, 1, and I'm going to go up in a way that is twice as tall. So instead of going 1 over 1 up, like I would for normal y equals x squared, I want to make that twice as tall. So 1 over 2 up. And I'll do the same thing on the left. 1 over 2 up. Then I just do my best to connect this into a steep U shape. So what we did in these last couple of examples is we looked at a formula for a quadratic in this vertex form. Again, it's called vertex form because it highlights where the vertex is. We looked at a formula in vertex form and figured out what the graph looks like. We can reverse that process. So suppose we have a parabola. Maybe we have a description for the parabola that's pretty accurate. Maybe we actually have a picture. Here's what we can do. If you have a good picture, you immediately know where the vertex is. So we can write the equation in a kind of vertex form, but we're not going to know what A is. Then what we'll use is we'll find any point besides the vertex. We'll plug in the coordinates for that point and solve for A. And we'll present that final formula. If you have a calculator, you can check as well. So here's an example, and you can just watch this. So a parabola has its vertex at 3, 7. So I'm going to draw a very rough picture here. A parabola has its vertex at 3, 7, something like so. And it passes through the point 12, 0. So it would look something, I'm just doing my best here to draw something that looks like a very wide U. So we know that this parabola is much less steep than the normal y equals x squared. Right? If it looks wider, it actually means that it's not as steep. But we can't just eyeball this and immediately say by what change. Right? If you're looking at this and saying it's half as steep or 1/3 as steep or 1/4 as steep, it's very, very hard to measure that precisely. So we need to actually measure it somehow. So here's what we're going to do. We're going to say if the vertex is at 3, 7, then I know this thing looks like y equals something times quantity x minus 3 squared plus 7. I know the vertex has been shifted 3 units to the right and 7 units up. So my formula looks something like this. And I temporarily accept that at least at the beginning of this problem, I don't yet know A. But I can solve for A because I know another point on this graph. So what I will now do is say, well, 12, 0 makes the equation true. To be on the graph means you make the equation true. If you make the equation true, you're on the graph. So 12, 0 makes the equation true. So let's insert those values. Everywhere I see x, I'll write 12. Everywhere I see y, I'll write 0. And it looks like 0 equals A times 12 minus 3 squared plus 7. 12 minus 3 is 9. 9 squared is 81. So we have A times 81 plus 7 Please note these are not like terms. Do not combine them. We can move the 7 to the other side. Negative 7 equals 81 times a, and a equals negative 7 over 81. That's a very specific number. There is virtually no way you can eyeball this graph and say, oh, you know what? It's exactly 7/81 as steep as the normal y equals x squared. All you can notice is it's much less steep and therefore wider, but getting that specific number requires you to actually solve an equation. And the equation we get, not a lot of room here because I should have added an extra page, but the equation for that parabola we described is y equals this very specific value of a times x minus 3 quantity squared plus 7. Now, if you're trying this for the first time, do this example. Parabola has its vertex at 2, negative 2 and passes through the point 0, 10. Draw a rough graph and find a formula. All right, my hope is that you have tried this. So I'm going to draw a rough picture here. 2, negative 2 would be something like so. And 0, 10 would be something like so. So we have a parabola like so. We definitely know where the vertex is. It looks like it's steeper than normal y equals x squared, but sometimes that's hard to tell. What do we know? We know it's been shifted 2 units to the right and 2 units down. So it has a pattern like this. I don't know what A is, so I will just write the letter A. But I definitely know that this part is x minus 2 squared because of where the vertex is, and this part is negative 2 because of the y-coordinate of the vertex. Now, to find A, we look for this other piece of information. I know if x is 0 and y is 10, the equation is true. So I can write 10 equals a times 0 minus 2 squared minus 2. 0 minus 2 is negative 2. If we square that, we get 4. So we have a times 4, or 4a, a minus 2 at the end. Again, do not combine those terms. Instead, add 2 to each side. So you have 12 equals 4a, and a equals 3. So our equation for this parabola is y equals 3 times x minus 2 squared minus 2. If you were doing this on a quiz and had your calculator, you really couldn't use your calculator to solve this problem, but you could definitely use it to check. You could plug this into your graphing calculator if you have time and check to see if the graph looks like this. Okay, practice problems are listed here, but that is the end of this section.